ATS113 students, it's time to talk about hurricanes. I love talking about hurricanes. As a tropical meteorologist, it's one of my favorite topics. And in this lecture, we're going to be learning about some of the fundamental challenges hurricanes face and how they solve them. We're going to learn some of the basics about like their size and their strength and how we name them and their tracks and where they form and all this good stuff. We're going to learn, of course, about their structure, the kind of things you're going to be seeing in your textbook in perhaps a little bit more detail. We're going to learn about the so-called hurricane cookbook, which is a way of describing what the atmosphere needs to have in order to form a hurricane. And then finally we're going to talk about the rather exciting topic of death and destruction in a hurricane. What are the causes of damage in a hurricane, and what parts of the world are more affected by hurricanes than others, and so on. Now, if I was just going to have to say I need a definition of the word hurricane, I'm going to say that it is a low-pressure system of tropical origin with winds of at least 74 miles per hour. Now, that number 74 miles per hour is not important. It happens to be a round number in the metric system. But it is a low-pressure system, and it is a different kind of low-pressure system than what we've seen so far. So far in this course, what we've been seeing are mid-latitude cyclones, which are areas of low pressure, and at the surface in the northern hemisphere they have counterclockwise rotation and so on. And hurricanes are also areas of low pressure, but they are of tropical origin. They also have counterclockwise in the northern hemisphere circulation at the surface and so on, but that's about where the similarities end. They're actually a very different creature that forms by a different process, not by cyclogenesis that we learned before and so on. They're quite different in a lot of important ways. Just to give you a sense, one way in which they're different is that their pressure tends to be a whole lot lower. If you remember that average surface pressure to the surface of the Earth is something like 1,013 millibars, a typical mid-latitude cyclone that comes through Omaha might have a pressure of like 1,000, maybe 995 millibars. A typical hurricane, though, has much lower pressure, more like 950 millibars, and the lowest hurricane pressures that have ever been observed are more like 880 millibars. So hurricanes, in general, are considerably lower pressure systems than mid-latitude cyclones are. Hurricanes, of course, produce enormous amounts of precipitation. In fact, they produce so much precipitation that they come across a fundamental problem that a lot of other weather systems don't encounter. Hurricanes produce so much rain, several inches an hour of rain can be a typical rain rate, that's kind of unsustainable. I mean, every drop of rain that falls out of the storm is water vapor that was in the atmosphere that got converted into liquid water. That's water vapor that is gone. And it isn't like the storm can run down to negative water vapor. I mean, once you have zero water vapor, or even close to zero, there's just no more forming clouds, forming raindrops, rain rates, and so on. So a hurricane has got a fundamental problem. It has to figure out how to get as much water back into the atmosphere as it is taking out of the atmosphere and dropping in the form of rain. Otherwise, in literally on the order of a few hours, the hurricane would run out of water vapor in the atmosphere. Therefore, a hurricane is going to need evaporation. We're going to need to have an enormous amount of evaporation coming off of the surface of the ocean to provide water vapor back to the hurricane so that the hurricane can keep feasting on all that water vapor and converting it back to liquid water and dumping it back on the surface. So we're going to need evaporation, and that's going to inform so many of our decisions about what hurricanes are going to do. But a big part of the story is this is why hurricanes have such strong winds. The strong winds make it possible to even have enough evaporation at the surface. The evaporation rate depends in part on the wind speed. So without that heavy those strong winds, you just wouldn't have enough evaporation. Now we're going to turn out it's also going to be related to things really on the hurricane cookbook and so on. But in order to have this at all possible, those big strong winds at the surface are a big part of the story. And because those big strong winds are a big part of what we fear about hurricanes, whether we're along the coast and we're worried about damage, or whether we're on a ship at sea or an oil drilling platform and so on, it turns out that works out to being a particularly good way to describe the hurricanes in terms of their strength. Now, you might remember we had the Fujita scale for tornadoes, which was based on damage. Obviously, hurricanes spend a lot of their life at sea. Well, we'll see why. Therefore, damage isn't really the key story here. So A number of different systems were tried over the years, but the one that has worked best is the so-called Saffir-Simpson scale that rates a hurricane. Once the hurricane reaches winds of at least 74 miles per hour, we call it a hurricane. Between 39 miles per hour and 74 miles per hour, we call it a tropical storm. Okay, you might be familiar with those terms from like watching the news or something like that. But again, the exact numbers are not what I'm going to be asking you on the quiz or something like that. But then we hit a Category 1 hurricane at 74 miles per hour, and then there's a Category 2 and Category 3 as the systems get stronger and stronger until you get all the way up to a Category 5 hurricane with wind speeds of greater than 155 miles per hour. And the strongest winds ever observed in a hurricane are somewhere in the neighborhood of, oh, I don't know, well, supposedly back in 2013, Typhoon Haiyan had winds of 195 miles per hour. There are some questions as to whether that observation is correct. And of course, Hurricane Katrina might be one that you're thinking about. At landfall, Hurricane Katrina had winds of merely 125 miles per hour, but way out in the Gulf of Mexico, she at one point had hurricane-strength winds at 175 miles per hour. Hey, by the way, real quick, just because I see a word on here that you might have been confused by, typhoon. Typhoons and hurricanes are the same kind of storms. Meteorologists didn't originally know that. It took until we had satellites and so on to realize that these storms were the same as the ones we were calling hurricanes. Typhoons are just what we call them when they're in the Western Pacific, whereas if they're in the Atlantic or the Eastern Pacific near the Americas, we call them hurricanes. So don't be thrown by that word typhoon. We're going to use the word hurricane and typhoon kind of interchangeably in this class, although strictly speaking, the word typhoon applies to ones in the Western Pacific. Hurricanes are smaller than you might think. If we were going to talk about the size of hurricanes, you look at it on a satellite picture and it looks pretty darn big. I mean, you'll often see on the Weather Channel in the peak of hurricane season, they'll show some picture of a hurricane that's taking up the whole Gulf of Mexico or something like that. No, it's not. Most of what you see when you look down on a satellite picture on a hurricane is just high cirrus clouds, like the anvils of the thunderstorms in the hurricane. The actual hurricane itself is no more than maybe a few hundred kilometers across, a few hundred miles across or something like that. You know, think a state or smaller, okay? Really, the center part of the hurricane, the eye wall that we'll be learning about in just a little bit, might only be as much as like 100 kilometers across. I mean, that's still bigger than a tornado or a thunderstorm, these kind of mesoscale features, but it is smaller than a mid-latitude cyclone. Remember, mid-latitude cyclones, the kinds that came through and brought weather to Omaha, they had a scale on the order of many states. They were synoptic scale weather features. Tornadoes do have stronger winds than hurricanes. You remember, tornadoes have winds of maybe like 300 miles per hour. Hurricanes, a really strong hurricane has winds of like 150. The vast majority of miles per hour. The vast majority of hurricanes are more like Category 1 at around 70 miles per hour. But tornadoes are much, much smaller than hurricanes. Tornadoes are no more than maybe a mile across. So the total kinetic energy in a hurricane is actually vastly greater. I forgot I had an actual slide about this, but just to be clear, this whole business of hurricanes and typhoons just is based on what part of the world we're talking about. And the idea in general is called a tropical cyclone. We don't worry in tropical meteorology about whether we're calling them a tropical storm or a hurricane or a typhoon. They're all tropical cyclones. They're all areas of low pressure with cyclonic rotation that are of tropical origin that work very differently than mid-latitude cyclones. Let's talk about something fun about hurricanes. Everybody loves the fact that we name them. In general, the way it works is we name them once the winds in the storm have been determined to have at least reached tropical storm strength, which is like 39 miles per hour or something like that, and we give them these names. We have different systems as to how we name the storms in different parts of the world. As it happens, we name them the same way, whether they happen in the Atlantic or the Eastern Pacific. It's the other parts of the world that have strange and very different systems. And as you probably know from watching the news or something like that, when we give hurricanes names or tropical storms names, the names are in alphabetical order. We start each year with a new list of names, and so the first hurricane of a particular year starts with A, and then the second one starts with B, and so on. Through the letters of the alphabet. We skip a few letters along the way. I don't think we use Q. I don't think we use Z. I forget. we alternate between male and female names, and we alternate which one we start with. So if we started with a boy's name the first one year, and the next year we'll start with a girl's name. So here's a list of, well, these are the names actually we use in the Atlantic right now. The way it actually works is we have 6 lists of these names, and we just rotate through these lists. So in 2022, we'll use the 2016 list again, and we just keep working through these lists. And so each year you can see we have these listed names. If you look at the names here, they might seem a little Europe-y. They may not seem quite like the names you would have picked for these storms. That is because these lists of names come from the World Meteorological Organization, which is part of the United Nations and is based in Switzerland. They're the general organization that provides guidance to like national meteorological services and so on, and they provide these lists of these names. So, I mean, these names do come from panels sitting in Switzerland, so it's not surprising that there's some rather French names on here. They're not coming from our part of the world. So that's why some of the names are a little bit peculiar. I do want to draw your attention to one weird thing about the list, and that is we can retire names from the list. If a particular storm was particularly strong or had a particularly large impact, the government of the country that was most affected by it or whatever can request the World Meteorological Organization retire that name, and it will never happen again. And you can see a fairly clear example of that. Hurricane Katrina was in 2005, and the name was retired. So in that, between then and 6 years later, which would have been 2011, they pulled out the name Katrina and put in Katja instead. And then so you can see that name is on the list for 2017 again. And there's other names missing there, as I noticed here. That was also the year of Wilma, Hurricane Wilma, and Wilma has been replaced by Whitney on this list. Okay. This is only one of a number of different ways that the Western Pacific names their hurricanes in a different system, and the Indian Ocean, they have names in different systems and so on. It's not even the first system we've used in the Atlantic. There have been a number of strange attempts to come up with naming systems in the Atlantic. For a while they were named after the phonetic alphabet, like what the military uses on the radio, Alpha, Bravo, Charlie. So they had like Hurricane Bravo and things like that. For a while they used the names of animals, believe it or not. So there was like Hurricane Antelope and so on. In fact, Hurricane Dog was a Category 5 hurricane. It went in the early 50s, I believe. There have been a number of strange systems, but we've used this system with boys and girls' names since the 1970s. And in fact, before that it was all girls' names, but it's kind of it's a story for a different day as to why we switched from using just girl names to just using boy names. You've probably noticed that I keep describing hurricanes in terms of oceans. And that's because hurricanes form over oceans. We're going to see why when we get to the Hurricane Cookbook part of the lecture. But if I kind of had just a diagram here that comes from a previous printing of your book, the areas that are shaded in orange are areas where hurricanes tend to form. You can see that all of these hurricanes are at fairly tropical locations, although strangely not at the equator. We're going to have to get a sense as to why that's happening. And you can see that they all pretty much track from east to west, because they're just being pushed by the trade winds. Remember the trade winds? Those winds at the surface that are from east to west in the tropics. For all their power, hurricanes are actually completely at the whim of the winds around them. They are just floating as the winds around them push them across the ocean. So in general, they just track from east to west. Now, if you look, those arrows that are on that diagram there show that at some point they tend to curve towards the pole. So in the northern hemisphere they curve to the north, in the southern hemisphere they curve to the south at some point. Not every hurricane does that, and that process has a weird name. That process is called recurving. I have no idea where that word comes from. Recurving makes it sound like it curves again, like it curved before and now it's recurving. I don't know where the word recurve comes from. But many hurricanes will recurve to the poleward direction as they progress, and I just happen to have 2 years of hurricane data up there on those plots right there. You can see that any given year is certainly messier than that long-term plot that I have there in the background, but overall they all kind of follow the same sort of pattern where hurricanes track from east to west across the Atlantic headed towards Central America and the United States, or if they form in the Eastern Pacific, they form out the coast of Mexico and track over towards Hawaii. That's just the path they take as they are being carried westward by the trade winds. Let's talk a little bit about hurricane structure. Your textbook does a fine job talking about this. Make sure you do read those pages in your textbook. And when you're reading those, if you haven't already, make sure you're watching for features like the eye and the eye wall and the rain bands and the circulation that's around the hurricane and so on. Let me just swipe a couple figures off the internet here to give you a sense of what we're looking at when we look at a hurricane. Here's kind of a slice through a hurricane, and what I want you to notice is that the structure of the hurricane is rotating at the surface in a cyclonic manner. In other words, in the northern hemisphere, it's rotating counterclockwise around the eye. The eye, of course, is a part of the hurricane that you almost certainly have heard of before. It is that relatively calm and clear center of a hurricane. Not every hurricane has a well-formed eye, but most of them do. It is the center of the low pressure. And the winds rotate around it in a cyclonic way at the surface. And they're very strong at the surface. But actually, as you get higher and higher up in the hurricane, the winds actually do get weaker and weaker and weaker. And about the mid-troposphere, they're very little wind at all. And then from there on up towards the tropopause, the winds get stronger again, but they actually are rotating the other way. At the top of a hurricane, the winds are actually rotating anticyclonically. So the hurricane has kind of a weird twist to it. At the bottom, it's rotating cyclonically, but at the top, near the tropopause, it's rotating anticyclonically. Weird. Mid-latitude cyclones aren't anything like that. Here's another way that they're different from mid-latitude cyclones. The center of the circulation, the eye, has sinking motion into an area of low pressure. That's weird. So for this semester, whenever we thought about low pressure, we thought about winds converging at the surface and rising in the area of low pressure. Now we have the opposite. We have sinking motion in the area of low pressure. Why? That's way complicated. We'd have to get into like the tropical meteorology course to get into that stuff. But it is sinking motion. That's part of the story as to why it's clear. Remember, when air parcels sink, they get warmer, they dry out, and so on. So the sinking motion in the eye is part of the reason why the eye is clear. Around the eye is a ring of thunderstorms called the eye wall. That's where the strongest rain is happening, that's where the strongest rising motion is happening, though that is where the strongest winds at the surface are. In fact, the strongest winds in a hurricane are at the surface in the eye wall. Okay, maybe not literally at the surface, I mean like within, at low levels, in the lowest 50 meters or something like that. So we see all these features here of this guy. I want to show you some more. Oh, here's another little cross-section I forgot I had on here. Now, notice how at greater distances away from the eye, we start encountering these sort of lines of thunderstorms that are called rain bands. And those rain bands kind of look like the arms of a galaxy or something like that. They look a little bit like fronts. But rain bands are not fronts. They do not separate one air mass from another or anything like that. There are no cold air masses and warm air masses around a tropical cyclone the way there are around a mid-latitude cyclone. In fact, that's another way in which tropical cyclones and mid-latitude cyclones are different. There are no different air masses associated with hurricanes the way there are with mid-latitude cyclones. But you do have those kind of bands of thunderstorm around the hurricane that are called rain bands. They're not fronts, but they kind of act a little bit like them. I want you to also notice the way they drew this cross-section here. I want you to notice how the eye is sort of wider at the top and narrower at the bottom. Another way to think about it is that the updrafts of those thunderstorms that make the eye wall are kind of tilted. That's a phenomenon with the cool name of the stadium effect. It's called the stadium effect because it makes the eye wall kind of sloped out a little bit like a football stadium or something like that, where it's narrower at the bottom where the good seats would be and wider at the top where the cheap seats would be. You can kind of get a sense of that in this photograph that was taken out the window of a Hurricane Hunter aircraft. You can kind of get a sense by looking at those clouds, how they're sloping away from you and so on. There it is narrower at the bottom as this aircraft is punching through the eye of the hurricane, and it is wider at the top. I mention this because it's a really interesting feature that once you know to look for, when you see satellite images of hurricanes, you're going to be able to see that this is actually happening. It actually turns out to be related to how strong the hurricane is. Hurricanes that are stronger have a bigger stadium effect and so on. But that's not where we're going with this. I just wanted to be able to describe that feature that we're seeing. Now, before we move forward and talk about more about why hurricanes happen and what you need to get a hurricane, let's answer 3 quick questions. Question 1. Why does the hurricane have strong winds? Why does it need to have strong winds? A, the strength of the Coriolis force depends on the speed of the wind, and the hurricane needs a strong Coriolis force. B, The strong winds provide evaporation at the surface to replace the water vapor that the hurricane is converting into precipitation. C. The strength of the force of friction depends on the speed of the wind, and the hurricane needs a lot of friction. Or D. A hurricane's strong winds provide the necessary rising motion in the eye. This question is a little more subtle than I originally planned, but I like it. Go ahead and make a choice from those 4 options and get a little feedback before you move on to question 2.